Question 1A then, part 1. Group 1 metals are known as the alkali metals. Now, it's important that you don't lose this mark easily. Sometimes people write alkaline metals and that'll be marked wrong, right? So it's not alkaline, it's alkali metals. And then on to part 2. Well, a property of all metals is that they are shiny. Now, reactive metals like sodium, potassium, they initially don't appear shiny because they react with oxygen and some moisture in the air, and they will go dull. But initially they are shiny, and if you cut them, you'll see that shiny surface. But after a few minutes, they go dull. And as I said, that's due to the reaction with oxygen in the air. Now, the word that describes shiny to dull is tarnish. But shiny to dull is all you need for the answer here. And then the least reactive element in group 1, and if we draw an outline of the periodic table, so we're thinking of this group. And for metals, the reactivity decreases as you go up the group. So that means that lithium is going to be the least reactive element in group 1, and the question asks for the symbol, so I have to put Li. Okay, on to part B. If an element has an electron configuration of 285, the group is going to be 5 because the group number equals the number of electrons in the outer shell. And I can tell from this electronic configuration that 5 is the outer shell, and so there are 5 electrons there. The period is 3. And I know that because the electronic configuration is 2, first shell, 8, second shell, 5, third shell. See part 1 then. Group not elements are known as the noble gases. So those are the elements away on the far right of the periodic table. So it's these ones here. And why are they unreactive? Well, that's because they have a full outer shell of electrons. And that full outer shell just makes the atoms stable. And that means that the noble gases do not need to gain or lose any electrons in order to gain a full outer shell. Okay, on to D then, part 1. Chlorine is a green gas, or you can say a yellow-green, not yellow on its own. That's more the colour of fluorine. And then iodine is a grey or grey-black colour, and it's a solid. The reactivity as you go down the group, for non-metals, the reactivity decreases as you go down the group, and that's the opposite to metals. Again, if I just draw a sketch here, there's a zigzag line to separate metals from non-metals. For metals, which are on the left of the zigzag line, the reactivity increases as you go down the group. But for non-metals, the reactivity increases as you go up the group. So it's the opposite to metals. So E part 1. You've got a displacement reaction for chlorine to potassium iodide. Well, chlorine is more reactive than iodine, so it displaces the iodine. Now, potassium iodide solution is colourless. And you should remember why it's colourless. Potassium is a group 1 element, and when you've got solutions of compounds of group 1 or group 2 elements, the solutions are always colourless. Now, when iodine is produced in the reaction, because it's an aqueous solution, it's brown. If bromine had been produced, it would have been more of an orange colour. And on to part 2. The half equation. Remember, half equations always contain E minus, either on the left or on the right. Now, this question asks us to convert iodide ions to iodine molecules. Well, iodide ions are I minus. An iodine molecule is I2. All the halogens are diatomic molecules. So Cl2, Br2, I2. Now we'll need to balance this. We've got 2 iodines on the right and only 1 on the left, so we need to put a 2 in front of the I minus. Now on the left hand side we've got 2 I minus, and that means then we've got a total charge on the left of 2 minus. But on the right hand side you can see that the charge is 0. So 2 electrons must have been lost. So we put 2E minus on the right hand side. So if you think of this here, so what has happened is we've got our 2 iodide ions, and I'm going to represent the extra electron here with a dot. So those are 2 iodide ions, and then those dots, so these electrons get lost, and then the 2 atoms join. So you end up with this diatomic molecule, and then you'll have your 2 electrons. So have a good look at that. Make sure you understand what's happening there. And on to question 2. A is a burette. Now be careful here. Do not say a biuret, which people sometimes do. That's a test for proteins in biology. Apparatus B is a conical flask. How could the pH be measured? Well, you could just simply use a pH meter. It's the simplest way to do that. I mean, you could, I suppose, have pieces of pH paper, and every so often you could have a glass rod and dip it in to the flask, and then keep dipping it onto the pH paper, and then match that with a colour chart. But a pH meter is just the simplest way to do that. Okay, why is it swirled? Well, that ensures complete mixing, and it ensures that the chemicals completely react with each other. Okay, then solution X. Well, solution X starts with a pH up here. Now you can't see it, it's cut off, but this is 12.0. Each small square is 1. So it goes 1, 2, etc. So it has a pH of 12 or 12.0. So that means it's alkaline. And then on to part 6. So we're now going to use the graph here to describe how the pH changes as acid is added to it. Well, you can see that the pH falls overall. And then you can see that initially on this part it falls gradually, and then there's a sudden decrease there. So this question is just asking you really to describe in fairly simple terms the shape of that graph. What do you see happening to the pH? Okay, then the ionic equation for neutralization. You should know this so that you can just simply recall it. Any neutralization reaction has the same ionic equation. There's going to be H plus OH minus. So the H plus is from the acid, the OH minus is from the alkali, and they react to form H2O. That's 2 marks. It hasn't asked for state samples, so I don't need to put those in. And then part 8, the volume of Y that's needed to react with X to form a neutral solution. Well, neutral is when it's pH 7. So you just need to go and read off the graph pH 7. It's around 11.5 cubic centimetres, and make sure that you have units in. Okay, so here are some qualitative tests. First one is a flame test, and we're told that sodium ions are present. Well, sodium ions produce a yellow colour or orange. If the second one, we're adding sodium hydroxide solution and followed by excess hydroxide solution, this is for zinc. Well, initially, a white precipitate forms, or you can say a white solid. And in excess hydroxide, that precipitate dissolves. And just to give a bit more detail on this white precipitate, here we would have zinc ions, which are Zn2+. They react with hydroxide ions to form an insoluble solid, which is zinc hydroxide. Now we need to balance this. You can see we've got 2 hydroxides on the right. So we need to put a 2 in front of the hydroxide on the left. So that's an ionic equation for the formation of that white precipitate. Now on to then the test 3. Some barium chloride solution. Well, when you see barium chloride being added to something, your mind should automatically think and be aware that that is testing for a sulfate. The barium chloride solution tests for sulfates. And again, we just get a white precipitate. Test 4, silver nitrate solution. Again, if that's a test, you should just be able to recall silver nitrate solution tests for halides. Always. And we've got chloride ions, so that means we're going to get a white precipitate. Now, the ionic equation for test 4. Well, the ion in silver nitrate solution, that is the important one, if you like, is the silver ion. And it reacts with chloride ions. Now, those are both soluble in water. Now, it hasn't asked us to put in state symbols, so we don't have to do that. But if it had asked for that, we'd have put in AQ, aqueous, to show that they dissolve in the water. Now, when those 2 ions come together, they form silver chloride, which is insoluble. And again, we don't have to put in the state symbol, but I'm putting it in just in case in a future question you are asked to do that. So the white precipitate is silver iodide. And it's the same general equation that you use for the other halides reacting with silver nitrate. So for example, if it had been a bromide, you'd have done Ag plus Br minus goes to give AgBr, which is cream precipitate. If it had been an iodide that was present, the ionic equation would have been Ag plus I minus goes to give AgI, which is a yellow precipitate. Okay, on to part 3. The formula of 2 different compounds which could be present in Z. Well, if we go back up to here, so Z contains these ions. We know from the flame test that there is sodium. Now that's asking for formula. So sodium, and then from test 3, it also contains sulfate ions. So one possible compound is sodium sulfate. you could have sodium and chloride. So that's test 1 and test 4. From test 2, there are zinc ions. So we could have a compound of zinc. And again, from test 3, you have sulfate. So combining test 2 and 3, we could have zinc sulfate. Combining tests 2 and 4, we could have zinc chloride. Now the valency of zinc is on the back of your data sheet. It's in that middle part of the periodic table. So that valency there, you'll see it's Zn and then a 2 after. So say that's on the back of your data sheet. Okay, now we're going to identify these different substances. Well, methane is CH4. That's going to be B. Ammonia is NH3. That's going to be D. Diatomic means 2 atoms covalently bonded together. Now, it's an element, so both of the atoms have to be the same. So that's going to be F. Nitrogen, which is N2. It's not HCl. HCl is diatomic, but it's not an element. And then for part 4, the chemical formula for D, well, NH3. Now we have to draw a dot and cross diagram for the bonding in C and E. And these are covalent compounds, so we just draw the outer shell electrons. So there's water, and then this is carbon dioxide, which contains a double covalent bond. There you are. So it contains 2 double covalent bonds. And remember, a covalent bond is the sharing of a pair of electrons. Okay, next question. Okay, now F was nitrogen, and it is a simple covalent molecule. So you should realize that all simple covalent molecules have low melting and boiling points for the same reason. So it doesn't matter in a sense that it's nitrogen. This answer will apply to nitrogen, to ammonia, to methane, to water, etc. There are weak forces between the molecules, and these weak forces are known as van der Waals forces. And because these forces are so weak, they require very little energy to break. And just to remind you of what that looks like, I'm going to draw out a couple of nitrogen molecules. Now this triple covalent bond does not break. It's very difficult to break that because it's so strong, and it would need a lot of energy to break it. But there are these weak intermolecular forces, intermolecular, so between molecules, and they're known as van der Waals forces. So these intermolecular forces are very, very weak. A covalent bond, when I mentioned that a short while ago, that's the sharing of a pair of electrons. On to part 8. So it's just a balanced equation for the reaction between hydrogen and chlorine. Well, hydrogen is diatomic, as is chlorine, and then they react to form hydrogen chloride. We need to balance that. So you should be able to see that we need a 2 in front of the HCl. And then the formula for ammonium chloride, well, ammonium is NH4+, which you'll find on the back of your data sheet. Okay, so that's NH4+. And then chloride has a valency of 1. Both of these have a valency of 1, so it's just NH4Cl. On to part B then, where we just have to complete. So I'm going to read the question carefully because it says it's information about ions. Okay. These are charged atoms that have lost or gained electrons. If something is plus, that means it has lost electrons. If something is a minus, that means it has gained electrons. Okay, first one has been done for us. Second one then is O2 minus. So that tells me that this has gained 2 electrons. The atomic number is 8. Well, the mass number of oxygen is found by looking up the periodic table. That's 16. The number of protons, well, the number of protons for oxygen never changes. It's 8. That's the same as the atomic number. Now, in an atom, which is neutral, the electrons would equal the protons. But remember, this is 2 minus, so it has gained an extra 2 electrons. So it's not 8 electrons in O2 minus, it will be 10. And the next one then, the atomic number is 19. Well, I can go then to the periodic table and find out what element that is. Well, that's going to be potassium. The number of protons is going to be 19 because that's the same as the atomic number. The number of electrons, 18. Now the electrons are not the same as the protons, so that means it's an ion. And I've got 1 extra positive charge. 19 protons, 18 electrons. So that means then for the symbol, I need to put a plus in there. And then the neutrons are worked out by subtracting the atomic number from the mass number. That's 20. Okay, then next one, number of protons is 30. Atomic number is going to be 30. The mass number, well, I add the protons and the neutrons together. That's 75. And then looking at the protons and the electrons, I see that there are 30 protons, 28 electrons. So 30 positives, 28 negatives. I have 2 extra positives. So this species, or this ion, is going to be 2 plus. Well, it has an atomic number of 30. And if I go to the periodic table, I find that zinc has an atomic number of 30. And I've already worked out that it has a charge of 2 plus. The next one then is scandium ion. So again, you go through the same sort of procedure to complete it and the next one. Okay, if you combine magnesium and oxide ions, that's just magnesium oxide. Now, why does that have a high melting point and conducts electricity when molten? Again, you should recognize that this is an ionic compound. So the question is basically asking you, why do ionic compounds have high melting points, and why do ionic compounds conduct electricity when molten? So again, in a sense, it's irrelevant that it's magnesium oxide. It could have been any ionic substance. It could have been magnesium chloride, sodium oxide, calcium sulfide, and so on. Well, ionic bonds are very strong and require a lot of energy to break. And that's why ionic substances have high melting points. And the other thing then you need to remember is that ionic substances only conduct when molten, when the ions are free to move and carry the charge. So it's not to do with electrons and ionic compounds, which it is in metals. So the answer then, for the first part, why does magnesium oxide have a high melting point? Those strong ionic bonds that require a lot of energy to break. And then the only conduct electricity when molten is because the ions can move and carry charge. Okay, we've just a couple of questions now to write out balanced symbol equations. Sodium hydroxide is NaCl. Sulfuric acid, which you should just know is H2SO4. That will go to give sodium sulfate and water, because we've got an acid and an alkali to give us salt and water. We need to balance that by putting in our 2's. The next one then is reacting copper to oxide. So copper is a valency of 2. That 2 tells us the copper is a valency of 2. And the oxygen has a valency of 2, so it's just CuO. We do not write Cu2O2 because those 2's will cancel. Plus H2SO4. This time the copper oxide is acting as a base. And an acid plus a base gives us salt plus water. It's going to be copper sulfate and water. There are 2 marks this time, so I don't need to balance it. There's 1 mark for the left-hand side, 1 mark for the right-hand side. Now, part C is asking us to prepare solutions. Now, just watch you don't misread the question. Sometimes a similar question to this would be to explain how you would prepare pure dry crystals. Well, you don't have to go on and explain how you obtain the crystals for this question. It's just asking how would you prepare a solution of sodium sulfate from sodium hydroxide solution and sulfuric acid. So we'll do that one first of all. Well, we'll need a set volume of sulfuric acid. For these types of reactions with acids and alkalis and so on, we tend to use around 25 cubic centimetres. So that would be a sensible volume to use. And I'm going to put that into some sort of container, like a beaker or a conical flask. I'm going to then need to know when I've added enough sodium hydroxide solution. So I'm going to have to put an indicator in here. So for example, I could use phenolphthalein. And then I'll add the sodium hydroxide solution until the indicator changes from colourless to pink. Now the next thing we'd have to do is remove that indicator, but we don't want it present in the solution. So then we would heat the solution with some charcoal, and then we'd filter it to remove the charcoal. Now we're going to move on to making a copper sulfate solution. So we're going to add the copper oxide to, again, 25 cubic centimetres of sulfuric acid. Again, you don't have to put in CuO, you can write it out as copper oxide. We're going to heat that. That just speeds up the reaction, or stir, you could say. And you add it until the copper oxide is in excess, and that just makes sure that all of the sulfuric acid gets used up. So here we have beaker, and we're adding our copper oxide, or copper oxide, which is black. So it goes in, and the solution obviously is copper sulfate, which is blue. But when all of the sulfuric acid gets used up, no more of that copper oxide will disappear, and we don't say dissolve. Right? So no more disappears or no more reacts. And you will find then that excess copper oxide just remains in the solution, which then has to be removed from it. So the next step then would be to filter it. And you filter it into a container. Often that is just an evaporating basin. So the solution then will come out a nice clear blue colour, and the unreacted copper oxide will get trapped in the filter paper. In D part 1, why is the solution not evaporated to dryness? Well, we're trying to make pure crystals. Now, crystals contain water of crystallization. So if we were just to heat the solution, so I'm going to draw the apparatus. So we've got our Bunsen burner, have our tripod, then we'll have our wire gauze, Then the evaporating basin, I'll just do it, evap basin. If you just evaporate off all of the water, the crystals that form will also get heated too much, and you would drive the water of crystallization out of the crystals. And so what would happen was that you wouldn't end up with crystals. You'd just end up with solid sodium 2 sulfate, or it'd be a powder. Okay, so we want to form crystals. They contain water of crystallization. So you do not heat, or if you do heat it too strongly, you will remove the water of crystallization. So that's why we evaporate off half, and then we leave the rest to cool and crystallize slowly. So there's another thing you could say there is crystals wouldn't form, or you just get a powder formed for that one. But prevent the removal of water crystallization is the best answer for that. The next one then, why do crystals form as the solution is cooled? Well, that ties in with the topic of solubility. So generally speaking, the solubility of solids increases with increasing temperature. So if you imagine we have our basin, the evaporating basin, with the copper 2 sulfate solution, and we've evaporated off half, and now we're just leaving it to cool. Because we've evaporated off half, we've obviously less volume of liquid. The copper 2 sulfate crystals will stay dissolved while it's hot, but as this here cools down, the copper 2 sulfate crystals cannot stay dissolved, and it'll eventually reach a cool enough temperature where the crystals do start to form. So just in simple terms then, the reason why crystals form as the solution is cooled is that the solubility decreases as the temperature decreases. Now, when we're drying the crystals, we do not want to remove the water of crystallization. So we could just use pieces of filter paper, and we need pieces of filter paper, or 2 pieces of filter paper, not just a piece of filter paper. And the other one we could use is a desiccator. Now, a desiccator is just a piece of apparatus that has some drying agent in it, like silica gel, for example, or anhydrous calcium chloride. And what that drying agent does is remove the moisture from the crystals. A third thing you suppose you could, or a third option, would be a low temperature oven. Now, we wouldn't obviously use a high temperature oven, because that would heat the crystals too much and it would drive out the water of crystallization. But if you use a low temperature, so it's just warm enough to dry the crystals, but not too warm so as to drive out that water of crystallization. So anyway, 2 of those 3 options is fine. In this question, we're having to work out the solubility of copper 2 sulfate. So what we're trying to determine here is the mass of the solid and obviously the mass of the water. Now, generally we don't use 100 grams of water because that would involve a lot of solid. So we use smaller quantities of water. So it just means then we require less solid to dissolve in that. So let's see if we can figure out how to work out the mass of the water. Well, the second result here is the evaporating basin plus the saturated solution. And the third one is the basin and the copper 2 sulfate after it has been heated. Well, that difference then must be due to the water. So if I do 38.45 minus the 25.95, that equals 12.5 grams of water. So you can see we're not using 100 grams of water. We're using 12.5 grams of water. I need to work out then the mass of solid that's in that 12.5 grams of water. So this time I'm going to subtract the mass of the evaporating basin from the evaporating basin and the copper 2 sulfate after it's heated. So that's going to be 25.95 minus 21.45, and that equals 4.5 grams. So we've got 4.5 grams of solid in 12.5 grams of water. Now we need to bring this up or scale it up so that we've got 100 grams of water, because that's what the question is, the solubility in grams per 100 grams of water. Now to go from 12.5 to 100, we multiply by 8. And that would mean you'd have to multiply the 4.5 by 8. If you weren't too sure of that, what you can do is just divide the 12.5 by 12.5, and that would give it 1 gram of water, and then you could multiply by 100. If you do that, then you have to divide 4.5 by 12.5. And then you multiply that by 100. And if you do that, you'll get an answer of 36 grams. Okay, you just work out the relative formula mass and then the number of moles. Number of moles equals the mass divided by the RFM. Obviously, do be careful with this one in particular. You have 17 carbons, 35 hydrogens, and then there's another carbon. So that's a total of 18. You've got your 2 oxygens, but you're multiplying then everything by 2. So you should work out this first, and then multiply that by 2, and then add on your calcium. Now in this question, we're having to work out the mass of water for crystallization. So basically what we're trying to do here is just heat the hydrated calcium chloride until there's no more water for crystallization left. And if we work out that difference, that'll be equivalent to or equal to the mass of water for crystallization. So this would be the apparatus we'd set up. We saw this on a previous slide. This here would be your hydrated calcium chloride. And we would heat that until there's no more change in mass. So that's heat to constant mass. And then if we subtract the final mass from the original mass, that would give us the mass of the water. So the first thing we'd do then is weigh an evaporating base that contained the hydrated calcium chloride. The next thing we'd do is heat to constant mass, because that means then that there's no more water for crystallization left. We'd then reweigh, and then we can subtract that final mass from the initial mass. So this here is the initial mass. So let's just check if we've covered everything. So include details of any mass measurements. Well, we have done that. And the equipment you would use. Well, I've drawn it here. So you could draw it and label it, or you write it down. Now, I've already mentioned the evaporating basin up there, so that would be one of the key things. So you could use a crucible instead of an evaporating basin. You don't use a lid, because the lid could trap some of the water. You're going to need a Bunsen burner as well, and then tripod, wire gauze, or a pipe clay triangle if you're using a crucible. And I think that covers everything to get your 6 marks. Here we've got like a reacting mass, a type of calculation. We've got 1.0 0.95 grams of the hydrated calcium chloride. So we divide that by the RFM. So imagine split up into two parts. So work out the CaCl2 mass, or RFM, and then work out 6 waters, 6 18s, and add the two together. And that gives you an RFM of 219. The number of moles is going to be 0.005. You can see that it's a 1-to-1 ratio, so that means it will produce 0.005 moles of the anhydrous calcium chloride. We can now then convert that to a mass. We just multiply that by the RFM of calcium chloride, which is 111, and that works out to be 0.555 grams. Okay, let's look at what the question asks. So calculate the loss in mass. Well, we started off with 1.095 grams. The mass now is 0.555. So the loss in mass is going to be 0.54. Now, it's not the only way of doing this experiment or this calculation. And what you could do, once you find out the number of moles of the hydrated calcium chloride, you could then look to see, well, how many moles of water are formed or are produced. Well, you can see it's a 1-to-6. Therefore, the moles of water will be 0.03. And then we can convert that to a mass. The mass equals 0.03 times the RFM of water, which is 18. And that also gives us 0.54 grams. Okay, percentage of water for crystallization. Well, we've already worked out the RFM of this hydrated salt is 219. We then need to work out the mass of the water. Well, we've got 6 waters. That's 6 18s. That's 108. So we just divide the 108, which is the total mass of the water, by the total mass of the hydrated salt, which is 219. So percentage, we multiply that by 100, and that is 49.3%.